A warm welcome to all the viewers. Friends, in this video, I'm going to specifically talk about how you can check univariate and multivariate normality if you are doing structural equation modeling, specifically covariance based structural equation modeling in IBM SPSS Amos. It works on maximum likelihood estimate. So, maximum likelihood estimate, which assumes that your data exhibits normality. So unless your data exhibits normality, you cannot go ahead with the analysis of the laid down model. So it becomes quite important to ascertain the univariate and multivariate normality so that you don't have any problems later on. In case the assumption of univariate and multivariate normality is not fulfilled, then there are certain remedial procedures to address this concern. Now, first step is you do a measurement model assessment, right? In measurement model assessment, you assess that whether your instrument of measurement, that is your survey which you have developed to collect the responses, is reliable or valid or not. So we check the reliability and validity of our survey instrument in measurement model assessment. We check whether all our latent variables, say this is latent variable 1, latent variable 2, linked to the reflective indicators. So you must remember that in IBM SPSS Amos, we cannot take formative constructs, we have to take reflective constructs only. Reflective constructs mean that all three statements pertaining to latent variable 1 are their effect statement and they all convey the same meaning in different words. So even if you remove one of the statements, if it possesses less factor loading, in that case it will not affect the meaning of latent variable 1. So that is known as reflective construct. So once you have, say for an instance, these two independent variables, each having three reflective indicators, and you have one dependent variable dv. In this case, in measurement model assessment, you draw the covariances, right? You draw the covariances, that is double headed arrows, which link all the three together to each other, irrespective of whether they are independent or dependent variables. Dependent variable also having three reflective indicators like this. So irrespective of being dependent or independent, we link all three with covariances in measurement model assessment. Now when we run this measurement model assessment, we estimate the factor loadings, these factor loadings, and check whether they are above at least zero point 0.7, and we also check the normality. So we are checking the normality as well, univariate and multivariate normality, because that is the essential to be checked for maximum likelihood estimation. So when you run measurement model assessment, you go to assessment of normality. Under this, you will get a tabular form in which all the indicators will be listed, and against these indicators you have the skewness value and its critical ratio, and then you have the kurtosis value and its critical ratio. Now we can check the univariate normality from these skewness values. It should range from -2 to +2. In case it is lesser than -2 or beyond +2, then we say that there is some issue of skewness. So we check it like this. If you want to check the critical ratio, it has to be within plus minus 1.96, so that we can ascertain that our data exhibits normality, because for a normal bell-shaped curve, the critical ratio, which is actually the z score, so this z value comes after dividing the skewness by the standard error. So this is the standardized value. So once you divide skewness value, absolute skewness value divided by standard error, you get the critical ratio. And this critical ratio for a normal bell-shaped curve should range from plus minus 1.96. Similarly, we assess the kurtosis. Now, this kurtosis value which is given to us by SPSS or IBM SPSS Amos, in both the cases, this is not the absolute value, it is excess kurtosis. Why excess kurtosis? Because a normal bell-shaped curve exhibits a kurtosis of 3. It exhibits a kurtosis of 3. So whatever value you get over here is beyond 3. In case it is going beyond 3, say for example plus 1.05. This means this is excess kurtosis beyond 3. If it is 3, it's well normal. It is a normal well-shaped curve. But for skewness, the value on normal curve is 0. It exhibits 0 skewness value. So that is why this is the absolute skewness value, but the kurtosis value is the excess kurtosis value. Remember this thing. In this case, we are certain that the excess kurtosis value should be between -2 to +7. Okay, it cannot go less than -2 and it shouldn't be greater than +7. Okay, so in case it lies within this -2 to +7, then you can say that your data exhibits normality. So this was about the univariate normality assessment, right? So just below this, in the critical ratio column, you get a single value which should be plus minus 1.96. This is the z-score. In case this is not plus minus 1.96 under the critical ratio column for the kurtosis, which is quite usual because your data might not exhibit perfect normality. It can only happen in case your data has perfect normality. In that case, you get plus minus 1.96 critical ratio. That is between minus 1.96 to plus 1.96. Below this kurtosis column, you get a score which is known as Mardia's coefficient. So this is known as Mardia's coefficient. So this Mardia's coefficient helps you to assess the multivariate normality. This helps you to assess the multivariate normality. This has to be less than 5. So in case below this kurtosis column you get Mardia's coefficient, this should be less than 5. In case it is less than 5, then you can go ahead and you can claim that your data exhibits normality. It has fulfilled the assumption of multivariate normality, as well as you have checked the univariate normality the way I have told you. So in the same table, assessment of normality, you are able to check both univariate and multivariate normality. Now what to do in case you don't get Mardia's coefficient which is less than 5? That means you don't have multivariate normality established. In that case, what to do? In that case, we go to see the Mahalanobis distance values. Mahalanobis distance values, which is calculated as Mahalanobis d square. Mahalanobis d square values. Now what is Mahalanobis distance values? Say you had several indicators, right, of independent variable and dependent variables for IV and DVs. You had those indicators, right? And if you plot these indicators in a space, say this is the space, you put the values of all these observed variables or indicators like this. So, and then you take out the mean of each observed variable. You take out the mean of each observed variable, manifest variable we also call it, or indicators. Then these means will coincide at some point. They will intersect at some point, say this point. So the means will intersect each other, and this is known as centroid. So the distance of data points, individual data points from this centroid is known as Mahalanobis distance, right? And there's a p-value associated with this Mahalanobis distance, which should be not lesser than 0.001. If the p-value is lesser than 0.001, that means that's a significant Mahalanobis distance. And by significance Mahalanobis distance, we mean that it will be an outlier. So if the p-value is less than 0.001, we say that observation or that respondent is might be a outlier, right? And we need to check that respondent's answers on our survey questionnaire and decide to eliminate that respondent from our survey because it seems to be an outlier. Say you had a data of 300 respondents, you will have the observation numbers listed down in descending order of their Mahalanobis distance. Then you have Mahalanobis distance, how far are they from the centroid, and then you have the P1 and P2 score. This is probability 1 and this is probability 2. Probability 1 means that it is the probability of a single randomly selected case having this large d square value, having this large t square value. The second P2 value tells us the probability of next largest d square value being large. Assessing data is normally distributed. Now, researchers and professors have recommended to look in for P2 values. Some have recommended to check in both P1 and P2. If both P1 and P2 are less than 0.001, say it is 0.000 and it is also 0.000, and this is distance. So in case this is 228, right? 28 point something. And then the next distance is, say, observation number 42. The distance is 11. Okay. So here you see a big gap. So this 204 observation might be an outlier. You need to check it because the P2 value is less than 0.001, that is probability is less than 0.001. Don't just remove them blindly, all those which are having the P1 and P2 values, in case both of them are having 000. One by one you have to eliminate and then run the analysis again to check the multivariate normality, whether Mardia's coefficient has improved or not. So if the Mardia's coefficient gets improved after removing the outliers, then you can claim that you have established multivariate normality and now you are good to go with maximum likelihood estimation in IBM SPSS Amos for conducting your structural model assessment. So this Mardia's coefficient has to be less than 5. Now friends, what if you don't achieve this Mardia's coefficient of less than 5? Even after removing the outliers, you don't achieve this value of less than 5. Then what to do? In that case, the remedial procedure is that you run a Bollenstein bootstrap, so as to check that whether your indicators are properly explaining the latent variable or not. If they are explaining the latent variable, then well and good. If they are not, then you have a problem establishing the validity of your instrument, and that's what we are doing in confirmatory factor analysis or measurement model assessment. So running Bollenstein bootstrap, you get a p-value which should be greater than 0.05. If this p-value is greater than 0.05, then you can go ahead with the structural model assessment. But again, in the structural model assessment, the second stage, where you replace the covariance double-sided arrows between the latent variables with directional arrows. Say this is independent variable and this is dependent variable. You replace this double-sided arrow with a single-sided arrow, that is a structural model, right? So you do that. And if you don't get the p-value less than 0.05 after running Bollenstein bootstrap, then you should stop your analysis because you are unable to establish the validity of your collected data, validity of your instrument, the survey which collected the data, and it cannot be taken ahead with maximum likelihood estimation as your data exhibits non-normality. There's one more estimation method available in IBM SPSS Amos, which is ADF, but that ADF estimation, which is actually asymptotically distribution free, requires a very large sample size, almost in thousands, 2000, 5000. It's not affected by non-normality, but it cannot take data which has missing values. But the beauty of maximum likelihood estimation here is that it forces the system to adopt FIML, that is full information maximum likelihood, in case your data has missing values. Automatically it does that. So that's why maximum likelihood is the preferred estimation method, default estimation method in IBM SPSS Amos, for which you need to establish the normality, univariate and multivariate normality. How to do that, how to check it, I've explained to you in this video. In case you are working with Jamovi has a estimation method which is known as MLR. So in MLR method, maximum likelihood robust method, this works even if the data is non-normal, and you can switch from maximum likelihood to MLR, which is not available in Amos. So in that case, you can go to Jamovi, conduct your analysis in Jamovi. For that, you don't even need to conduct Bolenstein bootstrap. If there's non-normality, checking the Mardias coefficient, it is greater than 5. So you change your estimation method to MLR, robust maximum likelihood, which is available in Jamovi software. Again, quite easy to conduct it in Jamovi. But if you are in SPSS Amos, then you must check it through Bolenstein bootstrap.